For estimating the bias of a coin, we saw in a previous video that the maximum likelihood estimate for the probability of heads was just the fraction of heads that we saw in the training data. For example, if our training data consisted of this sequence, heads, tails, heads, then the maximum likelihood estimate for the probability of heads would be 2/3. But you might say, there are only 3 tosses. That's not enough data to claim that the probability of heads is actually 2/3. The coin could still be fair, for example. And as another extreme example, if we only see one toss, for example, if we only saw heads, then the maximum likelihood estimate would be 1, because the fraction of heads is 1, even though there's only one toss. So this video briefly suggests an alternative approach, which is a Bayesian approach to learning parameters. In particular, instead of treating the parameter as some fixed unknown constant, the Bayesian school of thought instead treats parameter theta as a random variable. So rather than having this semicolon, we instead have our earlier notation of conditioning on theta, where now theta, so this is capital theta, is a random variable corresponding to the parameter of the distribution. Now we can impose some prior beliefs for what the parameter should be by choosing what the function p of capital theta is, where p of capital theta of little theta can be thought of as a non-negative weight for how much we prefer this specific choice, little theta, before observing any training data. As a technical note, p theta here is in general not like the probability tables we have seen so far in the course, because random variable capital theta has an alphabet that is the closed interval 0 to 1. This alphabet is neither finite nor countably infinite. Theta is actually what is called a continuous random variable. For the purposes of this video, though, you don't need to know the specifics of continuous random variables. Instead, it's enough to think of p sub capital theta of little theta as just a non-negative weight given to a specific parameter choice, little theta. So instead of maximizing the likelihood, so here I'll write theta hat sub ml for a maximum likelihood, now we'll instead maximize, we'll have argmax over theta within 0, 1 of the likelihood, which I'll now actually write out, so it's p of x1, x2, x3 of heads, tails, heads, and then here condition on parameter capital theta, so given data, so this is the likelihood. Now we'll actually try to maximize the likelihood times the prior on parameter theta, given by this function here. So the likelihood times prior. And the product rule for random variables actually says that this product here is actually the joint distribution of the training data, x1 up through x3 in this case, and capital theta, the parameter. So this is the joint distribution, and actually the argmax, treating the training data here, heads, tails, heads, as fixed, the argmax of the joint is the same thing as the argmax of, we have this joint again, so let me just copy it down here. So the joint divided by the probability of just the training data. Heads, tails, heads. Again, we're treating the training data we observed as fixed. So this thing here is the posterior. So this is just p of capital theta given x1, x2, and x3 of little theta given heads, tails, heads. So we're doing an argmax over theta of the posterior. And we've seen this earlier before. This is just theta hat MAP for maximum a posteriori. So I'm now going to show you two examples of this prior and work out what theta hat MAP is. So here's the first example where we have P of capital theta of theta is just going to be given by theta times 1 minus theta for theta within 0, 1. And so the MAP estimate in this case, theta hat MAP, is going to be equal to argmax over theta between 0 and 1 of the likelihood, which is theta squared times 1 minus theta. Okay, this comes from there being 2 heads and 1 tails in this heads, tails, heads example that we're still using. So we have the likelihood multiplied by the prior, which is theta times 1 minus theta. So this is, of course, theta cubed times 1 minus theta squared. And we've already seen how to maximize this. We take the log and we set the derivative with respect to theta to be equal to 0. But just by pattern matching, note that maximizing this is the same thing as doing an ML estimate when there are 3 heads and 2 tails. So the answer to this argmax is going to just be the fraction of heads where we have 3 heads and 2 tails, which is 3 over 3 plus 2, which is 3 over 5. And one way you can think about this is that here, this prior where we have theta times 1 minus theta, this theta is going to introduce a pseudo count of 1 head. And this 1 minus theta is going to introduce a pseudo count of 1 tails. Meaning that if you see NH heads and NT tails, then what this prior is going to do is actually going to make it seem like there are NH plus 1 heads and NT plus 1 tails. And then with this many heads and this many tails, it's just going to do the ML estimate for those tosses. So again, it's as if we introduced a pseudo count for heads and a pseudo count for tails, and then just did maximum likelihood estimation. To make that clear, I'll give a different example here where we have the prior is given by, so now I have this theta to the power of 100 times 1 minus theta to the power of 100. Again, with the observed sequence heads, tails, heads, the MAP estimate is going to be argmax over theta of the likelihood, which is theta squared times 1 minus theta, times this theta to the power of 100 times 1 minus theta to the power of 100. Okay, and this thing is going to be theta to the power of 102 times 1 minus theta to the power of 101. And so, again, we've seen how to maximize an expression like this. It is like maximum likelihood where we have 102 heads and 101 tails. So theta hat MAP in this case is going to be 102 divided by 102 plus 101. So in particular, this prior is basically making it look as if we're doing maximum likelihood, except where the number of heads is now the actual number of heads plus 100. So we have a pseudo count of 100 heads that are being introduced. And then we have the number of tails appearing like the actual number of tails plus this 100. And so for this particular case, in general, we would have theta hat MAP being equal to number of heads plus 100 divided by the sum of these two things, where NH plus NT is of course n, so we're going to have n plus 200. What this prior here is doing is much more so than the previous prior that we saw. When we have this 100 and 100, it's making it so that when the number of observations n is small, we're going to really think that the coin is probably fair. So this number down here, for example, this is pretty close to 1/2. So when the number of observations is small, we're going to essentially bias our estimate to be close to 100 over 200, because for nh and n small, basically the dominating terms are this 100 and 200, so this thing will be close to 1/2. However, when we crank up the amount of training data we have, n, then eventually when n is large and nh is possibly large, then nh and n are going to take over and dominate this 100 over 200. So the high-level idea is that for this Bayesian approach to learning parameters, we can neatly account for how much training data we have, where when we don't have that much training data, we trust our prior more, but when we have tons of training data, then we side with the data more, and basically our answer will look more like the ML estimate. So that is MAP estimation for learning parameters.